Very good afternoon, one and all. In the last class, we discussed the elements of PCM. Okay, so it consists of, as usual, for any like communication system, it too consists of PCM transmitter section, channel, and the PCM receiving section. Okay, so in the PCM transmitter, it consists of a low pass filter followed by A to D converter. Okay, so if you observe the low pass filter, it is mainly used to eliminate the problem of aliasing effect. Okay, so it by considering the sampling rate greater than or equal to 2 FM, by greater than or equal to 2 FM. Okay, so and it is followed by A to D converter. So A to D converter consists of 3 sections as we discussed. It consists of sampler, quantizer and encoder. Okay, so we already discussed the importance of sampler, quantizer and encoder. This sampling is used to discretize the time interval, okay, time axis, and quantizer divides the thing into the discrete continuous sample into discrete amplitude sample. Okay, and how many discrete levels it will divide? 2 power n number of levels. That is applied to the encoder. It generates the n-bit sequence based on the discrete amplitude, discrete sample. Okay, discrete amplitude sample. Next, that is applied to the channel, where the channel receives the noisy like distorted PCM it will receive, and that distorted PCM will be regenerated. Okay, that distorted PCM can be regenerated to get the original signal. Okay, and that is fed to the PCM receiving section consisting of decoder and reconstruction filter. This decoder is generally used to it possesses the opposite functionality of encoder, and this decoder is mainly preferred in order to regain the original analog format. And this reconstruction filter, like it is a low pass filter which based on the amplitude obtained by the output of decoder, it reconstructs and generates the low frequency component. Okay, this is all we studied in the earlier class. Okay, and later we have seen the importance of low pass filter. The input low pass filter eliminates the problem of aliasing effect. Okay, it like the overlapping of high frequency components with the with our data, with the low frequency signal, we can eliminate. Okay, this is all about the low pass filter, input low pass filter. And output low pass filter, that is at the receiving section, we have one more low pass filter that is used for reconstruction. Okay, and even we started the sampling. Okay, so sampling, what is the need of sampling? This sampler converts the analog signal into continuous amplitude sample. Okay, so mean that it discretizes the time. See, already we discussed that sampling rate should be greater than or equal to 2 FM to overcome the problem of aliasing effect. Okay, so the minimum sampling rate must be the Nyquist rate, which is equal to 2 FM. Okay, this everything we studied in the last class. Okay, so 3 types of sampling we started. One is ideal sampling, second one is natural sampling, third one is flat top sampling. And we already discussed that why the ideal sampling is called as impulse sampling and why it is also called as instantaneous sampling. Ideal sampling makes use of an impulse train. Okay, here let us take x delta of t as impulse train ranging from n minus infinite to plus infinite. Okay, so this what is x of t here? X of t is a band limited message signal. That band limited message signal is multiplied with x delta of t, where x delta of t is a impulse train. Okay, series of impulse train. So x of t is multiplied with x delta of t to generate the ideal sampled signal. This is also called as impulse sampling because it uses the series of impulses. Okay, so why it is called as instantaneous sampling? Because it occurs only at instantaneous levels, because the impulses doesn't possess any sort of pulse width. Okay, so it doesn't consist of any pulse width, because impulses are having a width of 0. So within a short interval, within a time span 0 interval, its magnitude goes to a maximum value. Okay, so because it occurs only at instantaneous levels, it is called as instantaneous sampling. Okay, so now here how can you, if you observe the first figure, you can say that if let us take the sample signal as xs of t, x suffix s of t, you can obtain the ideal sampled signal but just by taking the product of input signal with series of impulses. That's what it's shown in the like right side figure. So the right side figure shows you two signals. One signal is the analog signal, that is the input signal x of t, represented with dotted lines, and the pink lines represent, pink lines of varying amplitude represents the ideal sampled signal. If you observe the amplitude of the impulses, it is almost all like equal to that of message signal at the sampling intervals. Okay, its amplitude varies in accordance with x of t. Now let us see the time domain description. If you observe the time domain description, xs of t can be represented as the product of x of t and x delta of t. What is x delta of t? Series of impulses. So let del be the impulse function. So del of t minus nts. So the time instants are located at nts. Okay, sampling intervals occur at nts, where n ranges from minus infinite to plus infinite. So directly the product gives you the time domain description. And what about the frequency domain description? If you take the frequency domain description of the time shifted function, you will get an exponential term in the frequency domain. Okay, so like e power j n omega s t. Okay, so this is the frequency domain description of ideal sample signal, and this part we already studied in the last class. Okay, so what is the drawback of this ideal sample signal? So the main drawback here is that practically it is difficult to generate a series of impulses. Okay, and even it is like less compatible to the digital communication. And let us see the Fourier series representation. If the time shifted function can be represented as the product of exponential term in the frequency domain. Okay, so the main drawback is it is practically, it's somewhat, it is difficult to generate the series of impulses. So that's why natural sampling has been adopted. This natural sampling is the practical approach of ideal sampling. Okay, so what here we are doing, instead of impulse train, pulse train is considered, because some minimum width. Okay, so the here pulse width is tau is like very less width, less magnitude. Okay, pulse width is a minimum value, and that series of pulses will be practically generated. So the principle used here is same one. So x of t is multiplied with p of t to generate natural sampled signal. So what is x suffix s of t? The sampled signal. If you observe the waveform in the natural sample signal, if you multiply the series of pulses with x of t, the amplitude, okay, the amplitude of the pulses of the sample signal or output signal is not flat. It varies in accordance with input signal x of t. So that's why this kind of natural sample signal, because the amplitudes are not flat, okay, it is not compatible with the digital communication, because whenever the noise is accumulated at the tops of the signal, if it is continuously variable, it is difficult to like detach the noise from the signal. Okay, so that's why we like it's less considerable. This natural sampling technique is less considerable over the upgraded version, that is called as flat top sampling, where you can generate the amplitude of the pulses as flat instead of variable nature. Okay, so what is the drawback of natural sample signal? So the main drawback is the amplitude of the pulses of sampled signal is not constant, it is variable. Okay, so that's why it is not compatible with the uh, compatible with flat top sampling. Okay, so let us see the time domain description. How can we say the time domain description? Xs of t is equal to x of t into p of t. That is the time domain description of natural sampling. We can see it in the next slide. If you see the natural sampling result, the time domain description is xs of t equals to x of t into p of t, where p of t is the series of pulse train, rectangular pulse train. So because you are using rectangular pulses, it is also called as gating circuit. It is also called as gating circuit. Now, uh, and what is P of t? P of t is a rectangular pulse train, okay, which can be represented in the form of Fourier series expansion as summation n equals to minus infinite to plus infinite c suffix n into e power j n omega s t, where omega s is the angular frequency component, which can be represented as 2 pi f, and fs is the sampling rate, and c suffix n is the Fourier series coefficient, which you should evaluate while extraction of sample signal. Okay, so simply to say, the time domain description of natural sample signal is x of t into p of t. That's all. Okay. Now, how can you get the Fourier like frequency domain description? By applying the Fourier transform. If you apply Fourier transform to the actual signal, to the natural sample signal, what will happen here? Please apply Fourier transform x of t into p of t. Okay. So what is P of t? P of t is once again the summation of summation n equals to minus infinite to plus infinite, the Fourier series coefficient into e power j 2 pi n fst. If you observe here one point, in frequency domain, sorry, in time domain, the signal is multiplied with exponential term. In time domain, if the signal is multiplied with exponential term, you can obtain frequency shift in the frequency domain by the same factor. Okay, so that property is generally, that's from the Fourier transform property of frequency shifting. Okay, so that is from the frequency shifting property. If there is any multiplication with exponential term in time domain, the same can be replicated as shift in the same function in frequency domain. Okay, this is from frequency shift property of Fourier transform. Okay, like this you can represent the time domain and frequency domain descriptions of natural sampling. Okay, so I think up to this we discussed in the last class. So what is the main drawback of natural sampling? Because the amplitude of the pulses, because the amplitude of the pulses is of natural sample signal is not flat. Okay, its amplitude varies with respect to message signal. So it is not compatible to utilize it for a digital communication purpose. So that's why instead of natural sampling, flat top sampling technique is used. Okay, so if you observe the flat top sampling, it is generally obtained from the sample and hold circuit. It is obtained from sample and hold circuit. Okay, so we can discuss about this circuit in the next slide. And simply to say, this flat top sampled signal can be generated, you can generate it by taking the convolution of ideal sampled signal with the unity amplitude pulse train, with the unity amplitude pulse train. Okay, multiply a series of impulses with the message signal and take the convolution of that signal with the unity amplitude rectangular pulse. Okay, so like this you can generate the flat top sample signal, and it is generally obtained from the sample and hold circuit. Okay, so generation of the ideal sample signal is difficult, but we can generate the flat top sample signal by using sample and hold circuit. Okay, we can see the sample and hold circuit in the next slide. So this is flat top sampling. If you observe the left side first figure, okay, in the first figure you can observe the sample and hold circuit. Okay, In this sample and hold circuit, so how many elements are there? It consists of two switches. Please see the circuit elements and then we can see the working principle. Okay. So how many switches are there? Two switches are there. Those are G1, G2 and a capacitor called as hold capacitor. What is that capacitor C called as? Hold capacitor. Okay. So G1 switch is made on at which instance? At the instance of sampling intervals. At every sampling interval Ts, this G1 will be made on. Okay. So that is given by the ideal sample signal. Okay. So when G1 will be made on? G1 will be made on at sampling intervals. G1 will be made on at sampling intervals. That data can be provided by ideal sample signal. Okay, next G2 switch will be made on after every time duration of tau, where tau is the pulse width. Okay, here we are considering a pulse train and each and every pulse will have a width of tau. Each and every pulse will have a width of tau. So after every time interval of tau, this G2 switch will be made on. Okay. So let us see why this switch is called as discharge switch and G1 is called as sampling switch because that switch is made on at sampling intervals. Okay. So if you take x of t, so what is the input signal? Input signal is band limited message signal, okay, which is limited from -FM to +FM. Now that signal is applied to the this flat top sampling circuit or sample and hold circuit. Let us see the working principle. And you please observe the shunt capacitor. Here you are adding capacitor in shunt to the circuit. So I think everyone knows one point that the reactance of capacitor is inversely proportional to the frequency. Say yes or no? Yes, because XC is equal to 1 by 2 pi FC. Okay, so the reactance is inversely proportional to the frequency. So whenever the frequency as the frequency goes on increasing, the reactance of the capacitor will decrease. So for higher frequency components, the reactance is low. So of the capacitor is low. So that's why capacitor bypasses all the high frequency components to ground and allows only the low frequency component to the output section. That is the general idea. So shunt capacitor bypasses all the high frequency component to ground and frequency components will be allowed to the output section. Okay. Now let us see here. This is about sampling switch and discharge. Let us see the working principle. Please let us observe the working principle. So G1 will be made on at sampling intervals. And once G1 is made on, okay, so the capacitor, what it will do? Capacitor charges to the maximum extent of x of t via the sampling switch. During that time G2 is off. So what is the first point? Please remember that G1 is made on and G2 is made off. Whenever G1 is made on, capacitor charges via G1 up to the maximum value of x of t. And there is no path to discharge here. So that's why the maximum value is kept constant, or the capacitor holds the same value up to the instant of tau, because after the time interval of tau, G2 will be made on. After the time interval of tau, G2 will be made on. Once G2 is made on, what will happen? The capacitor discharges via G2 to ground. because during that time G1 will be made off. So here you need to remember 2 points. One is G1 on and G2 off. When G1 is made on, the capacitor charges via G1 and reaches to the maximum value of x of t. So that's why the pulse magnitude rises to x of t in the output waveform. And the capacitor output, okay, you can collect the output across the capacitor. The capacitor value, capacitor holds the same magnitude up to an instant of tau, because after the tau interval G2 will be made on. So once G2 is made on, automatically the capacitor discharges the magnitude to 0 via G2 to ground. Okay, so that's why you can attain variable, you can attain which kind of pulse samples here, flat top samples, okay, that occur at sampling intervals. And these all occur at sampling intervals. Okay, so that's why the capacitor here used is generally called as hold capacitor. So here two cases you need to study. One is G1 on and G2 off, and second one is G2 on and G1 off. When G1 on, capacitor charges and goes to the maximum value. If you observe the output waveform, whenever the capacitor is on, G1 is on, capacitor output magnitude increases to a maximum value, and it holds the same value till tau. After tau, what will happen? The G2 will be on, so capacitor minimizes to 0. Okay, this is the ideal representation of flat top sampled result. Okay, practically you will get some sort of discharging time. Okay, some time you need to require to discharge and some time you need to require for charge. So this is the ideal representation of the flat top sampled result. Okay, so this is how we can see the working principle, and after then what will happen? See, in the next slide we can see the working principle. In the next slide you can see the working principle. Is my voice audible to everyone? One of you respond.
Yes, ma'am.
Okay. Okay, thank you. So please, if you want to write down, you can write down. Whenever G1 is on and G2 is off, whenever G1 is on and G2 is off, then what will happen? Capacitor charges G1 is on and G2 is off. Output, the capacitor charges to the maximum value of x of t. And second point is the capacitor holds the same value. The capacitor holds the same value. Capacitor holds the same value till the time interval of tau. Till the time interval of okay, wait. Okay, please wait for 1 minute. Okay, you can see the working principle in this slide. Is this slide visible to everyone? Kindly one of you respond. Sample and hold circuit. The working principle. Is this slide visible? Flat top sampling, sample and hold circuit. Okay, ma, thank you. Okay, if you can see the three working principles. What is the first one? When G1 is made on and G2 is off, capacitor charges to the maximum extent of x of t and holds the same magnitude till G2 is made on. Okay, then the so whenever G2 is made on after the pulse width of tau, capacitor discharges the magnitude to 0 via short path of G2. Okay, so that's why in the output of flat top sampling, okay, you can observe the tops of the pulses as flat. Okay, so it is not variable as in the case of natural sampling. So that's why this kind of flat top sampling flat top sampled result is generally suitable for the digital system. Okay, so this is all about the sample and hold circuit. Let us see the mathematical representation of PCM. Let us see the mathematical representation of flat top sampled signal. Okay, so here let us take the output as usual as xs of t. X suffix s of t is the sampled signal, which sampled flat top sampled signal. So how can you generate a flat top sample signal? By taking the convolution of ideal sampled signal with unity amplitude rectangular pulse. Let us take that pulse as p of t as usual. Okay. So how can you generate xs of t? By taking the convolution of x dash of t. Okay. So x dash of t is the ideal sampled signal in convolution with p of t gives you the flat top sampling data. Okay. So what is x dash of t? Ideal sample signal. How can we generate ideal sample signal? We can generate ideal sample signal once again by multiplying the input signal x of t with x delta of t. With x delta of t. Okay, where x delta of t is series of impulse train. Please multiply x of t with x delta of t, you can generate ideal sample signal. And that ideal sample signal, it is kept in convolution with the unity amplitude rectangular pulse to generate flat top sampled signal. Okay, so replace p of t. What is p of t? Unity amplitude rectangular pulse. And what is x dash of t? Ideal sampled signal. We already know that ideal sampled signal is a product of x of t and x delta of t. X of t and x delta of t. How can you represent x delta of t? You can represent x delta of t, you can represent x delta of t as summation n equals to minus infinite to plus infinite del of t minus nts. Okay, where del represents the impulse function. And those impulses are located at nts. Okay, so what is the time domain description of flat top sampled signal? It is a convolution of ideal sampled signal with the rectangular pulse. Okay, how can you generate flat top sample signal? By taking the convolution of ideal sample signal with unity amplitude rectangular pulse. Here you should note that how can we generate ideal sample signal? Already we discussed the ideal sampling and we know it is the product of x of t and the series of impulses. Take that in convolutional with rectangular pulse. This process will be done by using sample and hold circuit, which we discussed in the last slide. Okay, so we can move to the next slide to identify the frequency domain description. Okay, let us see the frequency domain description. So apply Fourier transform. See, in time domain, we are taking the product of we are taking the convolution of the rectangular pulse with ideal sample signal. Okay, so in time domain, if you have convolution, the same thing will be replicated as product in the frequency domain. So that's why in frequency domain, if you apply Fourier transform to the time domain equation, you can get excess of omega as the product of the rectangular pulse and the ideal sample signal in frequency domain. What is P of omega? P of omega is Fourier transform of P of t. What is x dash of omega? Fourier transform of the ideal sample signal. Okay, just we replaced the ideal sample signal, okay, and rectangular pulse in frequency domain. And already we in the earlier slides we discussed what is x dash of omega. It is a frequency domain description of, or frequency domain representation of ideal sample signal. Already we have written it as 1 by Ts summation n equals to minus infinite to plus infinite x of omega minus n omega s. Okay. Okay. So that please observe the uh, spectrum. If you observe the spectrum, how will be the spectrum? The spectrum exists only at sampling intervals. So what are the sampling intervals? Fs, 2fs, like that. Okay, spectrum exists only at sampling intervals. Okay, sampling intervals 0 omega s, 2 omega s. Similarly, on the negative side, minus omega s, minus 2 omega s, like that, so on. This is the spectrum of flat top sample signal. Okay, how the time domain description will be? Time domain description consists of a flat pulses, okay, pulses whose amplitudes are flat, okay, with a pulse width of tau. That is the signal in time domain. In frequency domain, how it will be? It consists of a signal spectrum which exists at sampling rates. Okay, so the same representation in the form of equation is shown above. That is, excess of omega is the product of P of omega and the ideal sample signal. Okay, this is all about the flat top sampling. Now, so how can you define this sampling theorem? Okay, we can define it for low pass signals. This is the general statement, just I am recollecting for you. So how can you define sampling theorem? A continuous time signal can be represented in its samples and you can recover it back only when the sampling frequency is greater than or equal to maximum frequency component of message signal. Okay, so what it means? That is, Fs should be greater than or equal to 2 FM, then only the signal you can recover properly. You can recover the message signal properly at the receiver only when Fs is greater than or equal to 2 FM. Okay, this is for the low pass signals. For example, instead of low pass signals, if you consider the signal as a band, okay, band of frequencies, let that bandwidth be 2 FM. Okay, then how the statement will change? So the sampling theorem statement for band pass signals, okay, with a bandwidth of 2 FM, you can recover from its samples only when the sampling rate is greater than or equal to twice that of the bandwidth. But what is the bandwidth of the signal used here? 2 FM. So that's why Fs should be greater than or equal to twice that of the bandwidth. So bandwidth is 2 FM. So 2 into 2 FM. So it is equals to 4 FM. Okay. So this is the general sampling theorem statement. Now one of the student please respond. How many types of sampling techniques are there? Any one of the student. Please respond. How many
Ma'am,
types of చెప్పమ్మా చెప్పండి.
3 types, ma'am. Ideal sampling.
And ideal sampling, natural sampling, and the third one is flat top sampling. Okay. So what is the drawback of ideal sampling? Why we are considering, what is the difference between ideal sampling and natural sampling? Any other student please respond.
In ideal sampling, impulse train is used, and in natural sampling, rectangular gate signal is used.
Rectangular pulse train is used.
Pulse train is used.
Okay. But why we are not using natural sampling? Any other student, please respond. What is the drawback of
Ma'am,
natural
it
sampling?
is impossible. It is
Uh,
impossible to create a impulse time with very long time periods.
yes, its amplitude, the amplitude of the pulses continuously varies with respect to message signal. So it is like it is not compatible to use with the digital system. So that's why we are moving to the flat top sampling. And any one of you, can you explain the circuit of sample and hold circuit? Can you explain the working principle of sample and hold circuit, and how can we generate uh, the flat top sample signal? Sample and hold circuit. Generally, sample and hold circuit is used for generation of. Is this slide visible to you? Sample and hold circuit.
Yes, ma'am.
Okay. Okay. One of you please respond and tell me the working principle of sample and hold circuit, so that we can move to the quantization. Okay, because in your examinations you may get question regarding the sample and hold circuit. Okay. Tell me.
Ma'am,
Cheppamma, cheppandi. You can explain.
it consists of two switches and one capacitor, ma'am. The
Okay.
capacitor is shunt capacitor.
It is also
The two
called as
switches is
hold
sampling switch
capacitor.
and discharge switch. Yes, ma'am.
Yes, yes.
When J1 is on, the up to sampling interval TS, ma'am.
Oh,
At
yes.
that time, G2 is kept off, then the capacitor charges up to maximum extent, ma'am.
Yes.
So that the capacitor holds the fixed value.
Yes.
After that, after the time period T is completed, G2 will on for a
Yes.
pulse width of T, and G1 will off automatically, and the
Yes.
charge in the capacitor will comes to 0 from
Yes.
G2, ma'am.
Yes.
In that way, the sample and hold signal is created, ma'am.
So finally, you will get a samples whose amplitudes are flat. Okay, flat top samples you can generate with a pulse width of tau. Okay, and what is the time domain description? The time domain representation will be directly the convolution of ideal sample signal with the pulse train. Okay, so you can get the frequency domain representation by applying the Fourier transform. So instead of convolution in time domain, you can take the product in frequency domain. Okay, so this spectrum is shown here, which exists only at sampling intervals. To avoid the overlapping of the spectrum in frequency domain shown here, so you can observe the spectrum of flat top sampling here. So to avoid the overlapping, what is the condition? Always the sampling frequency should be greater than or equal to 2 FM. Then you can overlap the, then you can overcome the overlapping of higher frequencies with lower frequencies. Okay, so you can overcome the aliasing problem only when the sampling rate is greater than or equal to 2 FM. That is the basic sampling theorem statement, and that will differ based on the bandwidth. If the bandwidth is FM, Fs should be greater than or equal to twice the bandwidth. If the bandwidth is 2 FM for band pass signals, so twice that of 2 FM will be 4 FM. So Fs should be greater than or equal to 4 FM for band pass signals and 2 FM for low pass signals. Okay, now let us move to quantization. Okay, so before moving to the quantization, please note down the assignment for this week. Okay, so I request all the students to kindly note the assignment, and you try to solve it on Sunday. Okay, on Sunday, and you can submit it in the next week. So this is the assignment for this week. Sampling theorem proof for low pass and band pass signals. Anyhow, I will provide the material for the assignment after next week. One more week, I will wait for you. Okay, and I will provide you the data. No issue with that, but try for this. Okay, and we can move to. Ma, cheppandi.
I have a doubt, ma'am.
Okay, no problem. Tell me.
Yes, ma'am. Wait, ma'am. Sorry, ma'am. Flat top sampling lo rectangular pulse ni ideal sample తో కన్వల్యూషన్ చేస్తాం కదా మ్యామ్.
ఎస్ అక్కడ ఐడియల్ శాంప్లింగ్ అంటే జనరల్ గా పల్స్ విడ్త్ మినిమం పల్స్ విడ్త్ తీసుకుంటారు, అంటే నాట్ ఎగ్జాక్ట్లీ 0, సమ్ 0.1 0.2 అలా కన్సిడర్ చేసుకొని చేస్తారు, ఎందుకంటే ఐడియల్ మనం జనరేట్ చేయలేం కాబట్టి. అదేనా నీ డౌట్?
ఎస్ మ్యామ్, ఎస్ మ్యామ్.
ఐడియల్ జనరేట్ చేయలేం కాబట్టి అక్కడ కూడా సమ్ పల్స్ విడ్త్ తీసుకుంటారు. ఇంపల్స్ కూడా ఎగ్జాక్ట్ గా టౌ అనేది లైక్ 0 తీసుకోరు, సమ్ మినిమం వాల్యూ కన్సిడర్ చేసుకొని ప్రాక్టికల్ అప్రోచ్ లో యూజ్ చేస్తారు.
ఓకే మ్యామ్.
ఓకే,
Thank you.
అంతే కదా మీ డౌట్?
ఎస్ మ్యామ్, ఎస్ మ్యామ్. అదే
అదే అదే అర్థమైంది. ఓకే అమ్మా, అయితే ప్లీజ్ టేక్ దిస్ యాజ్ అసైన్మెంట్ అండ్ ట్రై టు కంప్లీట్ బై ద నెక్స్ట్ వీక్, or else I will provide you the material. So I will provide you the material for each and every assignment given for the week. Okay, this is the assignment for this week. Next, let us move to the next element. What is the next element of after sampling? After sampling, you can generate finally out of the 3 types of sampling techniques, flat top sample signal is preferred. So that is the conclusion. Okay, so that flat top sample signal is applied to the quantizer. So what will happen? So quantizer, that sample signal is nothing but continuous amplitude discrete time signal. Is it right? Okay, so you can define the sample signal as continuous amplitude sample. Continuous amplitude sample is the output of sampler. Okay, so next let us go to the quantizer. Okay, let us see what this quantizer will do. So quantization is a like what is meant by quantizer? Quantizer is a device and quantization is a process. Okay, so this device, what this quantizer will do? Quantizer converts the continuous amplitude sample. See, continuous amplitude sample is nothing but flat top sample signal. Okay, is nothing but the sample signal. Because you are using flat top sampling, you can say continuous amplitude sample as a sample signal, flat top sample signal. Okay, so quantizer converts the continuous amplitude sample into discrete amplitude sample. So what this quantizer do? It divides the amplitude axis into certain number of finite set of levels. How many set of levels it will divide? It will divide into 2 power n number of levels for a n bit sequence. For a n bit sequence, the quantizer divides the amplitude axis into finite set of levels equal to 2 power n. Okay, so in general, those amplitude levels are generally called as representation levels or reconstruction levels. Okay, or simply you can also call it as amplitude levels or discrete levels and kuda call change. Okay, so how can you call these discrete amplitude levels? You can call the discrete amplitude levels of the quantizer as either representation levels or reconstruction levels. And now each and every representation level, so we'll have some spacing. Ela divide chestaru? There will be some spacing between each and every amplitude value. That spacing is generally called as step size. Okay, so in your textbooks generally it is referred as step size. Okay, so the spacing between two adjacent representation levels is called as quantum or step size. Okay, so what is meant by quantizer? Quantizer is a device and quantization is a process. Quantizer performs quantization. Okay, this device performs some process. What is that process? It converts continuous amplitude sample into discrete amplitude sample. Okay, nothing but it divides the amplitude sample values of the sample values into 2 power n number of levels. Okay, for the n bit sequence. Now how many levels are there? 2 power n number of levels. For example, I am going to encode it into like 4 bit data sequence ankondi or 3 bit data sequence. Okay, so how many levels will be there? 2 power 3 ante 0 to 7, or instead of 0 to 7 you can also take it as from minus 3.5 to plus 3.5. Okay, so what is the step size there? With a step size of 1, unity step size. With a, anyhow, we can discuss in the next slides. In the unity step size, with the unity step size, you can take the levels from minus 3.5 to plus 3.5. Minus 3.5 to plus 3.5. Okay, if you consider the signal with the negative level and positive peaks. If the signal possesses negative peaks and positive peaks, then you can consider uh, the range from minus 3.5 to plus 3.5. So anyhow, the step size is 1 there, unity step size. Okay, so what are the amplitude levels? Generally called as representation levels or reconstruction levels. Okay, how many amplitude levels this quantizer divides the amplitude axis? 2 power n number of levels for n bit sequence. So quantizer converts continuous amplitude sample into discrete amplitude sample. Okay, this is about the quantization. Okay, let us the introduction to the quantization. Let us move to the next slide. In general, there are two types of quantization. Okay, one is uniform quantization, second one is non-uniform quantization. So what is meant by quantization? Quantization divides the amplitude, quantizer divides the amplitude axis into a certain number of levels. Those levels are called as representation levels. Okay, and what is the spacing between the representation levels? It is called as step size. You can also call it as quantum, but in regarding your textbooks, we can follow the term step size itself. Okay, so that step size, if it is constant, if it is uniform throughout the all representation levels, then it is called as uniform quantization. Nothing but its step size is fixed. Its step size is fixed for all the representation levels. For all the amplitude levels, if the step size is fixed, it is called as uniform quantization. Okay, if the step size is, it's not uniform. Okay, it is not at all uniform. Ante like from minus 3.5 to plus 3.5 to minus 2.5, the amplitude is 1. And from minus 2.5 to minus 1.5, the amplitude is 2. And from minus 1.5 to minus 0.5, the amplitude is 4. Based on the application, in some purposes, you need to consider the quantization levels as non-uniform only. Every time there is for all the applications, it is not sufficient to maintain uniform step size. In some applications, you need to take different amplitude levels for different step size for the amplitude levels or the representation levels. Okay, in general, that is assumed as, that's considered as a logarithmic. Okay, so mostly logarithmic nature is considered. Okay, that process is generally called as compounding. So what is a non-uniform quantization? That process is nothing but compounding process, compression plus expanding, where the step size is not at all uniform for all the representation levels. Is this slide okay to everyone? So how many, so what is quantizer? Quantizer converts continuous amplitude sample into discrete amplitude sample. How many discrete amplitude levels? 2 power n number of levels for n bit sequence. What are those amplitude levels called as? Representation levels. Okay, if the representation level spacing between all the representation levels is uniform, then it is called as fixed step size. If it is not uniform, then it is called as non-uniform quantization. Mostly we'll have logarithmic representation. Okay, for non-uniform quantization, the main example, the best example for non-uniform quantization is compounding process. Okay, that you can that we have seen in the syllabus. Okay, in the next class we can start up with the uniform quantization, the basic difference, and we can continue with the SNR calculation for PCM. Okay, so any doubts from the today's class? Meanwhile, I will take the attendance. F6, you can continue.
టచ్ చేసాను.
వాట్ మా F6 చెప్పండి మా ఏంటి?
పొరపాటు టచ్ చేసాను.
Okay. Thank you. Okay, if no doubts, we can wind up the session. So in the next class onwards, we can continue with the SNR calculation of PCM system by starting with the comparison between uniform and non-uniform quantization. We can, okay, so from the next class onwards, we can go through the basic difference between uniform and non-uniform quantization, and we can start up with the SNR calculation. Okay. Okay, I took the attendance. You can leave the session, no problem. So I will end the session. Okay, thank you.